So to explain you this entire concept, so if I explain you everything in theory oriented manner, you won't understand completely. That's why I play small videos. So after playing those videos, finally I will explain you the what are the important concepts behind that specific video. So today completely we will discuss the intuition of this thing. If time permits, we will discuss one artificial neural networks project. If time not permits, so we will discuss the project in the next session, that is on Monday session. So on Monday session, I will explain you two projects corresponding to this artificial neural networks, and I will give you one assignment project. So if you are interested, finish that assignment, or else I will forward you the solution also. Don't worry about that thing. So after that, in the Monday's class, we will start convolutional neural networks. So today we will start deep learning. So the main intuition of deep learning is to give human kind of behavior to the machine. To process huge amount of data, machine should think like a human being. So for that purpose, we are creating an artificial neural network. So that is called as, so the motto behind the entire deep learning concept will be, we need to train a machine like a human being. So for that purpose, we are taking concept called artificial neurons. So throughout that thing only we are moving. The intuition of that thing I will show you now. So we will see entire stuff.
Well, Allison should know. What is internet anyway?
Internet is that
Massive computer network.
So here it is not that much important content, but he explained how memory is evolved. So how day by day technologies are upcoming. That thing he explained clearly in this video.
the one that's becoming really big now.
What do you mean? That's big. How does one? What do you write to it like mail?
No, a lot of people use it and communicate. I guess they can communicate with NBC writers and producers. Allison, can you explain what internet is?
How amazing is that? Just over 20 years ago, people didn't even know what the internet was, and today we can't even imagine our lives without it. Welcome to the Deep Learning A to Z course. My name is Kilo Romenko, and along with the co-instructor Hadlan de Ponteves, we're super excited to have you on board. And today we're going to give you a quick overview of what deep learning it is and why it's picking up right now. So let's get started. Why did we have a look at that clip? And what is this photo over here? Well, that clip was from 1994. This is a photo of a computer from 1980. And the reason why we're kind of delving into history a little bit is because neural networks, along with deep learning, have been around for quite some time. And they've only started picking up now and impacting the world right now. But if you look back at the 80s, you'll see that even though they were invented in the 60s and 70s, they really caught on to a trend or caught wind.
Here it is that not that much important. See here he explained how memory is evolved. So that thing only he explained
in the 80s. Here. So you need to wait for it. Megabyte hard drive. That's 5 megabytes right there on the forklift, the size of a small room. That's a hard drive being transported to another location on a plane, and that is what storage looked like in 1956. You had to pay, a company had to pay $2,500 of those days dollars to rent that hard drive, to rent it, not buy it, to rent it for 1 month. In 1980, the situation improved a little bit. So here we've got a 10 megabyte hard drive for $3,500. It's still very expensive and only 10 megabytes. So that's like one photo these days. And today in 2017, we've got a 256 gigabyte SSD card for $150, which can fit on your finger. And if you're watching this video a year later or like in 2019 or 2025, you're probably laughing to yourself because by then you have even stronger storage capacity. But nevertheless, the point stands. So if we compare these across the board, and without even taking price and size into consideration, just the capacity of whatever was trending at the time. So from 1956 to 1980, capacity increased about double, and then it increased about 25,600 times. And the the length of the period is not that different. So from 1956 to 1980, 24 years. From 1980 to 2017, 37 years. So not that much of an increase in time, but a huge jump in technological progress. And that stands to show that this is not a linear trend. This is an exponential growth in technology. And if we take into account price and size, it'll be in the millions of increase. And here we actually have a chart on a logarithmic scale. So if we plot the hard drive cost per gigabyte, you'll see that it looks something like this. We're very quickly approaching zero. Right now you can get storage on Dropbox and Google Drive, which doesn't cost you anything, cloud storage, and that's going to continue. And in fact, over the years, this is going to go even further. Right now, scientists are already looking into using DNA for storage, and right now it's quite expensive. It costs $7,000 to synthesize 2 megabytes of data, and then another $2,000 to read it. But that kind of reminds you of this whole situation of the hard drive and the plane, that this is going to be mitigated very, very quickly with this exponential curve. 10 years from now, 20 years from now, everybody's going to be using DNA storage if we go down this direction. And here's some stats around that. So you can explore this further. Maybe pause the video if you want to read a bit more about this. This is from nature.com. And basically, you can store all of the world's data in just 1 kilogram of DNA storage. Or you can store about 1 billion terabytes of data in 1 gram of DNA storage. So that's just something to show how quickly we're progressing, and that this is why deep learning is picking up now, that we are finally at the stage where we have enough data to train super cool, super sophisticated models. Back then in the 80s when it was first initially invented, it just wasn't the case. And the second thing we talked about is processing capacity. So here we've got an exponential curve, again, on a log scale. It's not ideally portrayed here, but on the right you can see it's a log scale. And this is how computers have been evolving. So again, feel free to pause the slide. This is called Moore's Law. You've probably heard of it, how quickly the processing capacity of computers has been evolving. Right now we're somewhere over here where an average computer you can buy for $1,000 thinks at the speed of the brain of a rat, and by 2025 will be the speed of a human, or 2023, and then by 2050 or 2045 it'll surpass all of the humans combined. So basically we're entering the era of computers that are extremely powerful, that can process things way faster than we can imagine, and that is what is facilitating deep learning. So all of this brings us to the question: what is deep learning? What is this whole neural network situation? What is going on? What are we even talking about here? And you've probably seen a picture something like this. So let's dive into it. What is deep learning? This gentleman over here, Geoffrey Hinton, is known as the godfather of deep learning. And he did research on deep learning in the 80s, and he's done lots and lots of work, lots of research papers that he's published in deep learning. Right now he works at Google. So a lot of the things that we're going to be talking about actually come from Geoffrey Hinton. And you can see a lot. He's got quite a few YouTube videos. He explains things really well. So highly recommend checking them out. And so the idea behind deep learning is to look at the human brain, and there's going to be quite a bit of neuroscience coming up and in these tutorials. And what we're trying to do here is to mimic how the human brain operates. And we don't know that much, we don't know everything about the human brain, but that little amount that we know, we want to mimic it and recreate it. And why is that? Well, because the human brain seems to be one of the most powerful tools on this planet for learning, adapting skills and then applying them. And if computers could copy that, then we could just leverage what natural selection has already decided for us, all of those kind of algorithms that it has decided are the best. We're just going to leverage that. Why reinvent the bicycle, right? So let's see how this works. So here we've got some neurons. So these are neurons which have been smeared onto glass and then have been looked at under a microscope with some coloring. And this is, you can see what they look like. So they have like a body, they have these branches, and they have like tails and so on. So you can see then they have like a nucleus inside in the middle. And that's basically what a neuron looks like. in the human brain, there's approximately 100 billion neurons altogether. So these are individual neurons. These are actually motor neurons because they're bigger, they're easier to see. But nevertheless, there's 100 billion neurons in the human brain. And each neuron is connected to as many as about 1,000 of its neighbors. So to give you a picture, this is what it looks like. This is an actual section of the human brain, and this is the cerebellum, which is this part of your brain at the back. It is responsible for like motorics and for keeping your balance and some language capabilities and stuff like that. So this is just to show how vast, how many neurons there are. They're like billions and billions and billions of neurons all connected in your brain. It's not like when talking about 5 or 500 or 1,000 or a million. There's billions of neurons in there. And yeah, so that's what we're going to be trying to recreate. So how do we recreate this in a computer? Well, we create an artificial structure called an artificial neural net, where we have nodes or neurons. And we're going to have some neurons for input values. So these are values that you know about a certain situation. So for instance, you're modeling something, you want to predict something, you're always going to have some input, something to start your predictions off. And then that's called the input layer. Then you have the output. So that's a value that you predict, whether it's a price, whether it's is somebody going to leave the bank or stay in the bank, is this a fraudulent transaction, is this a real transaction, and so on. So that's going to be your output layer. And in between, we're going to have a hidden layer. So as you can see in your brain, you have so many neurons. So some information is coming in through your eyes, ears, nose. So you basically your senses, and then it's not just going right away to the output where you have the result. It's going through all of these billions and billions and billions of neurons before it gets to the output. And this is the whole concept behind it, that we're going to model the brain. So we need these hidden layers that are there before the output. So the input layers, neurons connected to the hidden layer neurons, the hidden layer neurons are connected to the output value. And so this is pretty cool, but what is this all about? Where is the deep learning here? Why is it called deep learning? There's nothing deep in here. Well, this is kind of like an
Take one simple example to understand this example. So let us assume you want to go to the movie. So to go to the movie, you are considering few constants, like whether with you bike is present or not, whether outside raining or not, whether your dad is giving permission or not. Let us assume you are considering these parameters, and these are called as inputs. These parameters, whatever the parameter you are considering, those are called as inputs. And for that, each and every parameter you are giving some importance. So for each and every parameter, you are giving some importance. That is called as weight parameter. So here, for the let us assume for the bike, you are giving 50% of importance. That means here I am giving 50% of importance to this neuron. And for dad's permission, I am giving just 20% of importance. That is the second neuron. After that, whether I have money or not, for that I am giving 30% importance. So like that, here we need to give importance to each and every neuron, so that that importance will be measured in the form of weights. The priorities are measured in the form of weights. So here these are inputs. Inputs will be said as x1, x2, x3, and whatever the importance which we are giving to those neurons, that will be said as weights, w1, w2, w3. So for these three neurons, we have three different weights. So here this one is called as hidden layer. So hidden layer is nothing but it is inside process. So here, as a human being, we can't analyze or we can't interpret this information. Machine only takes care about this entire information. That's why we are seeing this one as an hidden layer. Whatever the layer present between input and output, that will be said as hidden layer. And finally, we are getting output. So here in the output, we will get output like whether we went to movie or not. So here final output is whether we went to movie or not. That will be the R output. So to make you clear this thing, I will take one more example. Let us assume you are taking your hand near to the fire. So here, after watching at the fire, what happens? Your hand automatically comes back. What's happening there? So after looking that fire with your eyes, so automatically your hand comes back. So here input is, so we are moving our hand near to the fire. That is input. after seeing that fire with the eyes, our hands automatically comes back. So whereas after sensing the eyes, it will send information to the our brain. So after that, our brain send information to our hand in the form of neurons. Whereas here we are not visualizing all those steps. All those steps comes under hidden layer. So in the deep learning concept, if you have only one neural network, so here if you have only one hidden layer, that is called as normal neural network. Here in between input and output, if you have only one single hidden layer, that will call as simple neural networks. Whereas in between input and output, if you have more than one hidden layer, if you have more than one hidden layer, that will be said as deep neural network. So that will be said as deep neural network.
Which one might call shallow learning. There isn't much indeed going on. But why is it called deep learning? Well, because then we take this to the next level. We separate it even further, and we have not just one hidden layer. We have lots and lots and lots of hidden layers. And then we connect everything, just like in the human brain. We connect everything, interconnect everything, and that's how the input values are processed through all these hidden layers, just like in the human brain. Then we have an output value. And now we're talking deep learning. So that's what deep learning is all about on a very abstract level. In the further tutorials, we're going to dissect and dive deep into. Hello and welcome back to the course on deep learning. Today we're talking about the neuron, which is the basic building block of artificial neural networks. So let's get started. Previously we saw an image which looked like this, and quite an interesting.
So here it is a biological concept. It is not required to us that much depth. So here I'm cutting little bit portion.
This is what it's got. And so what are these dendrites for, and what's the axon for? Well, the key point to understand here is that neurons by themselves are pretty much useless. It's like an ant, right? An ant on its own can't do much. Like 5 ants together, maybe they can pick something up, but again, they can't build an anthill. They can't establish a colony. They can't work together as a huge organism. But at the same time, when you have lots and lots of ants, like you have a million ants, they can build a whole colony. They can build an anthill. Same thing with neurons. By itself, it's not that strong, but when you have lots of neurons together, they work together to do magic. And how do they work together? That's the question. Well, that's what the dendrites and the axon are for. So the dendrites are kind of like the receivers of the signal for the neuron, and the axon is the transmitter of the signal for the neuron. And here's an image of how it all works conceptually. So at the top, you've got a neuron, and you can see that its dendrites are connected to axons of other neurons that are like even further away above it. And then the signal from this neuron travels down its axon and connects or passes on to the dendrites of the next neuron. And that's how they're connected. And in that small image over there, you can see that the axon doesn't actually touch the dendrite. A lot of machine learning, or like a few machine learning scientists are very adamant about that, the fact that it doesn't touch. It doesn't touch. It has been proven that there is no physical connection there. But the point that we're interested in is that connection between them, that the whole concept of the signal being passed, that's called a synapse. You can see over there in that little image, that's figure bracket is a synapse, and that's the term we're going to be using. So instead of calling our artificial neurons, the lines that we're going to have, or the connectors for artificial neurons, we're not going to be calling them axons or dendrites, because then the question is, whose connection is this? Is it that neurons or is it this neurons? We're just going to call them synapses, and that's kind of just answers all questions right away. That's just basically where the signal is passed. Doesn't matter who that element belongs to. That's just a representation of the signal being passed, and we'll see that just now. So basically, that's how a neuron works. And so let's move on to how we're going to represent neurons, or how we're going to create neurons in machines. So we're moving away, now we're moving away from neuroscience and moving into technology. And here we go. So here's our neuron, also sometimes called the node. The neuron gets some input signals and has an output signal. So dendrites and axons, remember? But again, we're going to call these synapses. Then these input signals, we're going to represent them with other neurons as well. So in this specific case, you can see that this neuron, this green neuron, is getting signals from yellow neurons. And in this course, we're going to try and stick to a certain color coding regime where yellow means an input layer. So basically, all of the neurons that are on the outer layer or in the first front of where the signal is coming in. And by signal, it might be like a bit of an overkill to call this a signal. It's just basically input values. So you know how even like in a simple linear regression, you have input values and then you have a predicted value. Same thing here. So you have input values, and there they are, the yellow ones. And then on the right, you'll see just now, it'll be red. It'll be the output value. The thing that I wanted to point out here is that in this specific example, we're looking at a neuron which is getting its signals from the input layer neurons. So they're also neurons, but they're the input layer neurons. Sometimes you'll have neurons which get their signal from other hidden layer neurons, so from other green neurons, and the concept is going to be exactly the same. And just in this case, we, for simplicity's sake, we're portraying this example. And in terms of the input layer, the way to think about it is, in the analogy of the human brain, the input layer is your senses, right? So whatever you can see, hear, feel, touch, or smell. And of course, it's like there's a lot of things you can see. There's a lot of information coming in, but those are that's what your brain is limited to. It's pretty much it's pretty much lives in a box made out of bones, and it's only just it's a mind-blowing concept to think about, that your brain is just locked in a black box, and the only thing, like, it can't see, it can't hear, the only thing it's getting is electrical impulses coming from these organs that you have, which are called your ears, nose, eyes, your sense of touch, and whatever, and your taste, right? So it's just getting signals, but it basically lives in this dark black box, and it's making sense of the world through your senses. It's phenomenal. And so you have these inputs that are coming in. In terms of human brain, those are your 5 senses, and in terms of machine learning or deep learning, that is basically your input values, so your independent variables, and we'll get that to in a second. So your input values, the signal is passed through synapses to your neuron, and then your neuron has an output value that it passes further on down the chain. In this specific case, in terms of color coding, again, yellow means input layer. So we're kind of simplifying everything here. We're saying we're only going to have like the input layer, then we're going to have one hidden layer with the green, which is a hidden layer, and then we're going to have the output layer right away. So just so that we can get used to these colors for now. So there we go. That's the basic structure. So now let's look in a bit more detail at these different elements that we have. So we've got the input layer. And what do we have here? Well, we have these inputs, which are in fact independent variables. So independent variable 1, independent variable 2, independent variable m. And the important thing to remember here is that these independent variables are all for one single observation. So think of it as just one row in your database, one observation. You just take all of the independent variables, maybe it's the age of the person, the amount of money in the bank account, and then how do they drive or walk to work? What method of transportation do they use? So, but that's all descriptors of one specific person that you are either you're training your model on or you're performing some prediction on. The other thing you need to know about these variables is that you need to standardize them. So you need to either standardize them, which means make sure that they have a mean of 0 and a variance of 1, or you can also sometimes, and Hadlan will point out these situations in a bit more detail, perhaps in the practical tutorials you might come across these. Sometimes you might want to not standardize, you might want to normalize them, meaning that instead of making sure the mean is 0 and variance is 1, you just take, you subtract the minimum value and then you divide by the maximum minus the minimum, so by the range of your values. And there,
standardization is nothing but we need to perform feature scaling. That means we need to convert these features in the range of optimum range. So here for that we have different metrics. So here he's explaining about those metrics. We need not to take care about that thing. Simply we can apply standard scalar on it. Min-max standard scalar we have, as well as normal standard scalar, normalized standardization method also we have. So in normalization method, what happens means we will convert all the features in the range of -1 to +1 or -2 to +2. 2 like that. Whereas min-max scalar, min-max standardization is nothing but we need to convert all these features in the range of 0 to 1 range. So after that, after taking all these inputs, we need to add weights to these inputs. After adding weights to these inputs, here we need to consider whether we need to activate this neuron or we need to deactivate this neuron. For that purpose, here we need to learn about activation function. So here we need to take care of activation function. So we will discuss activation function in the next tutorial.
Where you get values between 0 and 1. And it's convolutional neural network, who we already mentioned. So in this paper, or will stay, or it can be a categorical variable. And
so coming to the deep learning, also same thing. We can work with the continuous data as well as categorical data also. So whereas if your problem is the binary classification problem, so there we can use binary cross entropy function to predict the outcome. So whereas if it is a categorical problem, so for that we need to use categorical cross entropy function. We will discuss that thing while discussing the program. So here output might be a categorical value or else continuous value.
If it's a categorical variable, the important thing to remember artificial neural network rename observation. So important to remember that like whatever inputs you're putting in, that's for one row, and then the output you get, that is for that same exact row. Or if you're training your neural network, then you're putting the inputs in for that one row, you're putting the output in for that one row. So probably like if you want to simplify the complexity, think of it as a like a simple linear regression or a multivariate linear regression. So you're putting in your values, you have your output. There's no question about it when we're talking about things like regression, because we're so used to it. Same thing here. It's nothing too complex. We're just putting in values, we're getting output, but just remember that every time it's one row you're dealing with, so you don't get confused and start putting in like thinking that these are different rows that you're putting into your artificial neural network or something. This is all just values in that one row. So different observations, different characteristics of or attributes relating to that one observation every single time. Okay, so next thing that we want to talk about here is the synapses. Here we've got synapses, and they all actually get assigned weights. Weights, we're going to talk more about weights further down, but in short, weights are crucial to artificial neural networks functioning, because the weights are how neural networks learn. By adjusting the weights, the neural network decides in every single case what signal is important, what signal is not important to a certain neuron, what signal gets passed along and what signal doesn't get passed along, or to what strength, to what extent signals get passed along. So weights are crucial. They are the things that get adjusted through the process of learning. Like when you're training an artificial neural network, you're basically adjusting all of the weights in all of the synapses across this whole neural network, and that's where gradient descent and backpropagation come into play, and those are concepts that we'll also discuss. So signals go into the neuron, and what happens in the neuron? So this is the interesting part. Like we're talking about the neuron today. What happens inside the neuron? So a few things happen. First thing, and the first step, is that all of these values that it's getting get added up. So it takes the added, so the weighted sum of all of the input values that it's getting. Very simple, so right? It's very, very straightforward. Just
two parameters. First one is the inputs. Those are nothing but x1, x2, and xm. After that, we need to give importance to the weights. Weights are nothing but how much priority you are giving for each and every input. So here, how to assign this weight randomly, we will discuss in the next tutorials, or after finishing all the tutorials, I will explain you how to take these weights. So after that, here it is the formula for output. So here we need to add all the weights with multiplying with the inputs. That is nothing. If you take this example only, here what we need to do here, output is nothing but w1 x1 plus w2 x2 plus so on dash wm xm. So here it is the output equation for this specific thing. So after this, in this neuron, what we need to do here, we need to apply activation function, whether this neuron contributes, so whether this neuron give output or not. So here that is nothing but output, give output or not means here output is 1 or 0. For that purpose, here we need to use activation function. As I already forwarded you the next class video, link in the group. join in the video. I will explain you that thing.
To this neuron or to this whole layer, and it is applied to this weighted sum, and then from that the neuron understands if it needs to pass on a signal, if it, like that's the signal that it passes on, that the function applied to